right, good morning. Well, welcome back. So, my plan for today is to talk a little bit more about arrays and look at their order of complexity for operations and use that as a motivation for developing a new type of array called a linked list. And we're going to talk about the basic high-level behavior of a linked list, and then we'll start thinking about how we can write code to implement a linked list to organize information. And then before class ends, we'll take a look at the programming assignment, which was posted yesterday, and will be due in about a week and a half. So any questions before we start? And we're missing half the class, but oh well. We've got to jump into this. I'm going to make a decision tomorrow about whether next week will be back to being in person or continue being remote. My feeling right now is unless something significant happens in the next 24 hours, we're going to stay remote for next week also. Because, yesterday we had 1 million new cases reported and today 800,000, and things are just not looking like they're going in a good direction this week. So, but I'll make a decision and post something on Canvas tomorrow, definitive, to let you know what week 2 is going to be. All right, so let's go back and look at arrays. And remember, we started talking about order of complexity, and with order of complexity, we're thinking mainly about how computation time changes as the size of a problem grows. And so we thought about an array. So there's an array of 8 numbers, and we said if we want to search, this is really order n. If there's no, order to this, if this is just a collection of things stored in memory and we want to search for the number 18, we could, look around randomly. We might get lucky and find this, or we might be looking for a 4 and find it right in the beginning. But in general, we've got to basically just look at every element in the array. In particular, if the number we're looking for is not in the array, it's going to take us n operations, right? Assuming we have n pieces of data. So search on an unordered array is going to be order n. And then we said insert. We can just, add something to the end of the array. That's basically order 1. And delete. Well, we can delete the 6, for example, by just moving the 200 up to take the place of the 6. But we still need to find where that 6 is so that we know where to make that change. So this is, basically order n because the search is order n. And so we want to do better than order n. We want to be able to do something that's not going to, quadruple in time every time we quadruple the amount of data. We'd like to do better. So we're shooting for something like log n. And so what can we do to this array in order to speed up our search? This is something we did in the very beginning of 224. Although we didn't phrase it like that. But if you think about your high-low game, that's basically a search problem. The person you're playing with is thinking of a number, and you're searching all the numbers between 0 and 100, for example, to find their number. And if you just say, is it 1, is it 2, is it 3, is it 4, it might take you 100 guesses to find their number. But we did something different, right, when we played high-low. So what was the thing that we did to be able to guess a person's number in fewer than, say, 100 guesses?
Cut the data down with every guess.
Yeah, we chopped the size of the problem down with every guess. So this is something called divide and conquer. It's a class of algorithms that we'll encounter frequently. And it's basically saying, I want to solve this problem. Let me split it into a smaller problem. And I'll spend some time and energy splitting it into a smaller problem, but hopefully the smaller problem is quicker to solve than the time I spent splitting it into that smaller piece. And when we play high-low, each time we make a guess, if we pick a good guess, we cut our problem in half. And so if we're trying to find a number among 100 and we split our problem in half 7 times, we're trying to find a number out of, one possible number. And we can definitively say, okay, your number is 17. The reason we can do that is because the things that we are searching, that set of numbers from 0 to 100 that we're playing the game with, we can think of those as being sorted, right? And the sort is coming because we don't just guess a number and the person says yes or no. The person says, my number is lower than that or higher than that. So if we... Say again?
This only works if the array has already been sorted from high to low, though, correct?
This only works if the array has been sorted from high to low, or low to high. So let's rewrite this array, and I should have picked some easier numbers.
Should make a new one.
There we go. I think I got it. So if our data happens to be stored like this, we don't need n operations to search for something. We can play high-low. So let's say we're searching for the number 18 again. Well, we pick a number in the middle, 7. And 7 is too small. So we don't have to look at any of these numbers anymore. We only have to search this smaller array containing 3 or 4 things to look for the number 18. And if we start right in the middle, 18, hey, we found it in only 2 operations. If we're searching for the number 17, we'll say, okay, is it this one? No, it's bigger than 7. We'll throw those away. We'll try 18. It's smaller than 18. We'll throw these away. We've only got one number left. Is 11 the number we're looking for? No. 3 operations, we can say your number's not in the array. So if we keep our data sorted, our search gets really nice. It becomes log n. And log in these kinds of notations usually means logarithm base 2. So if our array is sorted, search becomes order log n. And that's really nice. But we've introduced a new complexity. What happens to our insert time? Suppose I want to insert the number 12 into this array. What do I have to do?
Find where it belongs or add it and then sort it again.
I can either add it and sort it again. Sorting is usually really expensive. Or, I could say, hey, the 12 belongs right here. I'm going to move all of these things down. And I'm going to put my 12 right here. Which is effectively, inserting and sorting. But sorting is usually, at least n log n. This would be an order n operation. Worst case, for example, suppose I want to insert -10. Well, where does the -10 go? It's really got to go right here. It's got to become the first thing in the array because it's the smallest number in the array. And I can't put a -10 here because I've already got a -5 there. And I don't want to lose that number, so I would have to move the -5 over here. But I can't do that because there's a 2 sitting there, so I have to move the 2 out of the way first. This is not hard to code, but it's time consuming. Basically what I would do is I would start with the last number and I would move it down 1 spot. And I would take the next number and move that down, and so on. And then I would have an open spot to insert my new number. But our insert just became order n. And deletion is the same problem. If I want to delete, let's just go back to this version right here. Let's say I want to delete the 7. Well, I can no longer do that slick trick of just taking the last thing and putting it in there. That was our order 1 delete. But I can't do that because my array will be out of order. If I want to delete the 7, really what I have to do is move the 11 up there, and move the 18 here, and move the 200 up here. And so delete is going to be order n also. It's actually going to be n plus log n, because I still need to find the thing I'm inserting or deleting. You know, find the right spot in here. But n is so much bigger than log n that these end up just being order n. So punchline, right? We can improve the search speed by sorting the array, but our insert and delete speeds kind of go out the window. And if you're planning to do a lot of searching on your data, but your data is not going to change, storing your data in a sorted array, really good thing to do. It's very efficient, it's very easy to implement. But if you're going to be continually adding to and removing from that set of data, these things are going to be performance killers. And so we want something that lets us store our data in something like an array, but does a better job with dealing with inserts and deletes. So let's look at how we can improve that performance. And let's think about an array. So there's 5 things stored in an array. And let's think about, again, the memory of the machine from the perspective of the CPU. And let's think about how an array is implemented. So we have an array called data, and we want to access elements like it. We need to know 2 things. We need to know where the array begins. What's the memory location where this first piece of data is stored? If we don't know that, you know, all bets are off. We also need to know, once we found the beginning of the array, where's the next element in the array? So we need to know where the array begins, in other words, where this first element is. But we also need to know, if we know where one element is, where's the next element? Alright, so here's the thing. Arrays have a fixed structure in memory. Where the array begins, well, that's the value of this variable data. If we make an array called data, D-A-T-A, the value of that variable is the address in memory where the first element is stored. So that takes care of the first requirement. Where's the next element? It's the previous element plus however big the thing is that you're storing in the array. So let's suppose our array begins at location 100 hex. If this is an array of integers, and assuming an integer takes 4 bytes, we're guaranteed the next element in the array is at location 104. The next element will be 108, the next element will be 10C, the next element will be 110, and so on. And that's how arrays work. That's why arrays work. Because if I want to get to the nth element, I can take n, multiply by 4, add it to the starting address. That's the address of the nth element. So if our data array starts at location 100 hex, then data bracket n is at 100 hex plus 4 times n. So it's a simple calculation. And in your compiled code, if you look at the assembly language or machine code from your C program, if you have something like a reference to data bracket n, you'll find code that basically takes n, multiplies by 4, adds that to some address, which is where your array begins, and uses that as the address for data bracket n. All right, so that's an array. Go ahead.
Put it into the next memory address instead of this weird.
Sorry, say that again? I missed the beginning.
Why doesn't it just put it into like the next memory address, like just one above it or below, instead of?
You can do that with characters, but with integers, for example, you need 4 bytes to store an integer.
Oh, okay.
Right, so if this was like, 2 billion something, we would need full 32 bits to store that. But for characters, it does exactly that. If we have an array of characters, first character is at 100, the next would be at 101, and then 102, and so on. If you have an array of doubles, that's going to use every 8th location, because a double takes 8 bytes. So this is one reason why we like using size of, so that we don't have to know, what the magic number is that these spots get incremented by. All right, so this is very simple for a compiler to implement, right? And we don't have to think about it as programmers. We just say data bracket 5 or data bracket I, and the code, is written for us to access the right thing. The downside of doing this, though, is that, the locations where each of these things are stored are fixed. And wherever the 7 is stored, the 11 is stored in the next location in memory, plus 4 in this case. And if we're trying to insert an 8, well, the 8 should really go in between the 7 and the 11, but there's no space for it. Right? So here's an 11, and it's written as, in hex, 32 bits. And here's the 20, which is written in hex. Looks like 1-4, right? Well, this is what's at location 8. This is location 9, 10, 11. This is location 12, 13, 14, 15. They're contiguous in memory. And if I want to insert a 15, there's no space to put it in. It's a fundamental limitation of arrays. And because of that, if we want to insert, we have to move things down, and that's where the order n comes from. And if we want to delete, we have to move things up, and that's where the order n comes from. So we have an idea. And the idea is to break this dependence on where each element of the array is stored, so that it's not always just this simple formula of taking your index, multiplying by the size of your object, and adding to the base. So let's get rid of this. Let's see, could you change the address of the elements in the array to move the integers in the array for an insert command? You could. That's effectively what you do when you shift everything down or up. But that's something you're going to have to do to each element that has to move. And if you have n elements, that's n operations. So that's another view of where the order n comes from. So we're going to do something really slick. We're going to make a new type of an array, and this is called a linked list. So let's take a set of data. Let's take a 2 and a 4 and a 7 and a 12 and a 19. And instead of storing these in consecutive memory locations, and relying on the fact that, this is stored at location 100, 104, 108, 10C, 110, and so on, I'm going to store an extra piece of information with each number. I'm going to store the number 2, but then I'm also going to store the address in memory where the next number is located. And at that next number, I'm going to find the number 4, but I'm also going to store next to that the address in memory where the next number is located. And so I'm going to store 2 pieces of information for each integer. I'm going to store the integer itself, but I'm also going to store the address in memory where the next number is stored. So let's look at a memory map, and let's suppose, we started location 100. And let's just put some numbers in here. We'll assume this array is sorted, right? So we'll start with a 2 and a 4 and a 7 and a 12 and a 19. And maybe, my data happens to be stored in consecutive locations, but I'm not going to rely on that. What I'm going to do is, in addition to storing a 2, I'm going to store the location in memory where the next number is. So when I get to the 4, I'm going to say, hey, the next number is 7, that's at location 108, I'm going to store 108 here. And the number after 7 is 12, that's at location 10C. And location after 12 is 19, that's stored at location 110. And these are hex numbers, that's why I've got like C's in there and why I'm going by 4s. These are hexadecimal numbers. So if you're not still familiar with hexadecimal, go back and refresh that. Right, so 104, 108, 112 basically. And this 19 is the last thing in the list. Right? There's no number after that. So what should I put here? I mean, if I put, 114, that's basically saying, oh, there's a number after 19, whatever number is stored here. But I'd like to have a way to be able to just look at this set of data in memory and know that there's nothing after 19. That's the last thing. So I'm going to store a special number here. Yeah, I'm going to store a 0 here. And this is why it's important that memory location 0 is not valid. Because if I decided, I'm just going to store 1,000 to mark the end of my array, well, what if I had a number stored in location 1,000? But you're guaranteed there's never a number stored at location 0. So if I put a 0 here for the address of the next number, that's a flag. That's not actually a memory address. That's a special flag saying, hey, this is the last thing in the array or in the linked list. And we don't store a 0, we actually use a symbol called null. And null is defined for us inside an include file that we'll use in C programs, and null is basically equal to 0. But we'll use the word null to mean memory location 0. Alright, so this captures the same information as our original array, which just had, 5 things stored in the first 5 locations. As long as we know our list starts here, we can say, okay, so the first number is 2, the second number is 4, the third number at 108 is 7, that's followed by 12, that's followed by 19, and bonus, we know that that's the end of the data. So there's only 5 pieces of data. All right, how do we insert into this list? Suppose I want to insert a 3. Well, if this is an array, the 3 has to go right after the 2 and before the 4. We would have to move everything down in memory. But in a linked list, we don't have to move a whole lot of stuff around to do an insert. What we really want is we want our 2 to point to a 3. And we want 3 to point to the 4. And so even though we have all of this stuff in our list, all we've got to do is make a change right up here. It doesn't matter if there's a million numbers down here. Just have to make a little change up here in this part of the array. Alright, so here comes the magic. Watch this. You're going to do this like a billion times this quarter. So here's time number 1. Let's insert a 3 into this linked list. Well, we've got to store the 3 somewhere. I'm just going to store it here because that's an available location. And I want it to come after the 2. And I want it to come right before the 4. Alright, so how do I indicate that this 3 is followed by the 4? I say, hey, the number after this is the number stored at this location, 104. And how do I indicate that this comes right after the 2? I go up to here where the 2 is stored and I say, hey, the next number is the thing at location 114. And we are done. And we've inserted a number into this list. And we only had to do 2 things. Right? Create this new number with the address of the thing that comes after it, and change the thing before it to point to that new number. So let's look at what our array looks like now. Assuming it begins at location 100, the first number is a 2. What's the next number? It's down at location 114. It's a 3. What's the next number? It's at location 104. That's a 4. What's the next number? It's at 108. That's a 7. What's the next number? It's at 10C. That's a 12. What's the next number? It's at 110. That's a 19. What's the next number? There is none. That's the end of the list. Alright, you really want to understand this algorithm before you start writing code. We're going to write code to do this inside the computer, but before you ever start, saying vi functions.c, you want to make sure you understand on paper what you're trying to do. So you're going to want to get, a whiteboard or a big sheet of paper, good eraser and pencil and so on, and you're going to want to do this by yourself. Make yourself a memory map, store some data in there, and now do things like say, hey, I want to insert 15. Okay, well, how do I do that? First, you have to find where the 15 should go. So start at the beginning of the list. There's a 2, so it comes after that. That's followed by a 3. It comes after that. That's followed by a 4. It comes after that. That's followed by a 7. 15 comes after that. That's followed by a 12. It comes after 12. That's followed by a 19. Hey, we just found the number that's supposed to come after 15. We're supposed to insert right before this location. Well, I need to remember what the previous location was. The previous spot I was at was right here. Remember, I was at this location. I looked at a 12. I said 15 comes after a 12. So I went to the next number down here, found a 19. Hey, 19 comes after what I'm inserting. So first thing you have to do is find the 2 numbers you want to insert in between. In this case, I want to insert between here and here. Now I'm going to make a new piece of data, and I'm going to find some location in memory that's available. Let's just suppose it's 118. I'll put my data there. And the thing that 15 will point to should be whatever number is going to come after 15. Well, we found that. It should be the 19. So I'm going to say, hey, the number after 15 is the number at location 110. And then the number right before the thing we're inserting, we change that. So instead of pointing to the 19, it points to our new number. So we change this to 118. Bingo, we're done. We inserted a 15. And we can check our list again. We start with a 2, followed by a 3, followed by a 4, followed by a 7, followed by a 12, followed by 15, followed by 19, and that's the end of the list. So our data is still sorted, but it's only taking a fixed number of operations to insert our number into the list. So this insert operation is going to go from order n to order 1 to do the actual insert, but order log n to find the insert place. So insert's going to become log n. Almost. The real story here is that our search time is going to degrade. With a linked list, our search is going to go back to order n. And so ultimately in a linked list, our insert and delete times are going to be order n, but that's only because of the search. And in a few weeks, we'll bring our search back to log n, and then our insert and delete will also be log n. And then we'll be happy. That's when we're talking about binary trees. But for now, we're just thinking about once you know where you want to insert or delete, can we speed up that operation? And the answer is yes. Once we know that we're inserting between here and here, it's a fixed amount of steps to do that insert. We don't have to shuffle things around in memory. Oh, I've got a billion questions in chat. You should use your microphones when you have questions, because I'm not really staring at my chat a lot these days. Let's see. Aren't arrays static so that the memory after an array may or may not be reserved? That's correct, and we don't want to do this with an actual array, right? We could make an array, you know, with 1,000 entries and just use locations like this, but we're not going to do that. We're going to use that malloc statement every time we want to create a new piece of data. We're going to use malloc to find a piece of data big enough to hold our integer and our pointer to the next number. So we'll be using dynamic memory. You do not need to do attendance pings. I'm not taking attendance this term. Okay, yeah, that's cool. How do we check where 3 goes? How do we know it goes between 2 and 4? So you have to do this, you have to walk through your data starting from the beginning and stop when you get to the first number that's bigger than what you're inserting. Right? And so this is going to be significant when we start coding this.
Do you have to cache the beginning member of the linked list?
Yeah, you've always got to know where the list begins. So yeah, we should write these down. 1, remember where the list begins. Because if we don't know that, we're out of luck. And then when you insert, find the first number bigger than what you're inserting. But as you're moving through the data and finding that first number that's bigger, you have to remember the previous number. For example, when we inserted the 15, we got down here to the 19, we said, okay, it should go right before the 19. We needed to know what the number was right before that, though, because that number is going to change to point to the 15. So as we march through our data, we've got to kind of keep track of like where we are, but also where we were one step earlier. So yeah, that could be a for loop or a while loop. Probably a while loop, checking to see if the number is greater than the thing we're inserting. And yes, this is still order n, but it's slightly better than an array because if we can speed up the search, this will become order 1. And eventually we'll modify our linked lists to make searches faster. But right now, yeah, if we want to search for a 15, we got to start at the beginning and follow the links and follow the links and follow the links until we find a 15, or we get to the end of the list and we didn't find our number. But we will speed that up in a few weeks, and then we'll have order log n across the board.
Is there any case commits on Canvas?
Say again?
Is are listed, these commands on Canvas.
What commands?
Never mind.
Okay. All right, so we're going to draw a lot of pictures in this course, and you want to find a way to draw pictures of things that make sense to you. When I first learned linked lists, it took me, you know, a couple of weeks, I think, to figure out a way to draw pictures of a linked list that made sense to me. And they were different from how my teacher did it. They were different from how some of my friends did it. You got to find a way that makes sense to you. But I'll always draw them kind of the same way here. But find your own way to code this information if you like. But let me show you a picture of what this linked list might look like. So typically we draw, you know, a box, and we have our data, and then we have a pointer to the next thing in our list. And then this last one, if this is the last thing in the list, we'll just write a null down there. And we're thinking of this as, you know, here's a piece of data, and here's a pointer. It's another piece of data. It's an integer. It's a big integer that actually represents the location in memory where the next block is stored. And this is the main thing we'll be using pointers for the next few weeks. We'll use a pointer to basically tell us where the next block is stored in memory. So now if I want to insert a 4, what am I doing? I'm creating a new block. I'm saying that wherever the previous block was pointing, in other words, the thing that should come after the 4, I want my 4 to point to that. So I'm going to set this next field of this new node to point to that 5. And then I'm going to change the next field of the previous node to point to my new node. And now if I want to know what my data looks like, it's a 2 followed by a 3, followed by a 4, a 5, a 20, and a 30. And it doesn't matter if this block is sitting, you know, over here or on the other side of my computer or, you know, somewhere else. As long as I store the address of it right here in this part of my 3 node, right? My 3 will point to the 4, and the 4's next field will point to the 5. And these can be anywhere in memory, and they don't need to be sequential at all. And oftentimes they won't be. All right, other questions?
I'm kind of curious if you were going to show us this in code, because I'm wondering how this is going to be implemented.
Yeah.
To the beginning of that.
So we'll get to code in a little bit, and then we'll be able to talk about programming assignment 1. But I want to explore these algorithms and pictures a little longer. And
How would you add to the beginning and the end?
So adding to the end is not a problem. If we want to insert a 40, well, we just make a new block. We put a 40 on there, and we change our 30 to point to that, and we set 40 to point to null to say that's the end. So adding to the end is not actually an edge case, but adding to the beginning is. If we want to insert a 1, well, we need to create a new node with a 1 and have that point here, but remembering where the list begins becomes a challenge now. Now we need to know that our list begins with that 1 instead of with the 2. And that's going to bring in something that we call a sentinel node, and so we'll come back and talk about that in a few minutes also. And we'll see a way to make that a non-issue. All right, but first, let's think about deletion. So let's go back to this picture of memory, and let's say I want to delete a 7. So I'll find the 7. I'll start with a 2. I'll follow it to the 114 is a 3. I'll follow it to 104 is 4. I'll follow that to 108 is 7. Here's the thing I want to delete. Alright, and just like before, I'm going to need to know this is the thing I'm deleting, but I also need to remember what the previous node was. And deleting is even easier than inserting. To delete, all I do is I see where this node's pointing, just change the previous node to point there. And we're done. Alright, why is that a delete? Because if I look at my data now, I start with a 2, that's followed by a 3, that's followed by a 4, 4 is followed by 10C, that's a 12. We went straight from 4 to 12, we skipped over the 7, it's been deleted. Now, it's not removed from memory. We can never remove memory. There's always something stored in every location in memory. And this 7 happens to still be sitting here, but it's not part of our list anymore. That's the sense in which it's deleted. And
But
that's...
it's still there.
It's still there.
If it's still there, then is it just, you can always create an address to refer back to it, right? Like, anytime anyone.
Yeah, and that's actually an interesting security question. If you're storing information in a linked list and you delete something like this, the thing you deleted can still be sitting in memory. If it's a password, it might still be there. And somebody else might be able to go and take a snapshot of memory and find this thing that you think you deleted.
This is how like FBI and whatnot can scrape hard drives.
Yeah, yeah. Exactly the same idea. When you delete a file, you don't actually remove the stuff from the hard drive, you just stop referring to it. Well, same thing here. We're not removing the 7, we're just not referring to it. We're saying, hey, after a 4, let's go down to a 12. And we jump over it. Now we could... Say again?
I'm kind of curious about if this is how, you know how like computers have this like recovery mode, you go back in time and recover files? I wonder if it's that same kind of idea where it's not actually removed, but it's just no longer referred to, like you mentioned earlier.
Yeah, so that's how file recovery programs work. So if you delete something from your hard drive, it doesn't, unless you shred it, right, it really just, it leaves everything there, it just stops referring to it. But if you haven't done a whole lot on your hard drive since then, you can go back and you can figure out where that was stored and you can make a reference to it and get your file back. If you try to do it, 6 months later, chances are something else has used that spot of the hard drive. And with this, if we keep inserting and deleting, chances are something else will get stored here eventually. But if you're quick enough, right, you may be able to recover information that you deleted. If you don't want that to happen, you use something like a shred program. And when you shred a file, instead of just removing the reference to it first, it overwrites the information in that file. So that even if you go back and you find a way to refer to where that file was on the hard drive, now you find gibberish.
Just overwrite it with a 1 and then free it.
Yeah, although if you just overwrite with a single bit pattern, you can still go in and analyze the structure of the hard drive and recover the information that was there. Because hard drives are a physical medium, and when you write a particular value, you change, the magnetic polarization of the little iron particles on the platter, and if you analyze those carefully enough, you can say, okay, before this was changed, was it, north-south or south-north? And so if you want to securely shred a file, you need to do things like write alternating patterns of 1s and 0s a certain number of times. So you write a bunch of 55 hexes and a bunch of EEs hexes and things like that. And there's all kinds of specifications you can find out there. There's the DoD Orange Book that tells you how many times you have to write these different patterns in order to securely shred a file based on, the classification level of the data and so on and so forth. It's a really interesting world, and if you get a chance to take a security course, you can get into all these kinds of details. And it's
If you delete that from the linked list, but you want to delete it from memory and return the memory to the random access memory.
So you could in your code that's doing the deletion, before you change this pointer to be a 10C, you could say, okay, I'm just going to write a 0 into this location. And you know, hopefully that makes it impossible for someone to go back and look at that location and say, hey, there was a 7 stored there. All right, so we can insert by creating a new node and adjusting our pointers. We can delete by simply adjusting our pointers. And if we go back to our picture and we want to say, you know, delete a 20, effectively all we're doing is taking this, and instead of having the previous node 5 point to 20, have 5 point to whatever 20 is pointing to. Well, we've just deleted 20, and it doesn't look like it because I can see the 20 right there. But if I look at the data in my list, it's a 2, a 3, a 4, a 5, a 30, and a 40. There's no 20. It's gone. When we use malloc, we ask the operating system to give us a block of memory. When we're done with a block of memory, we're going to use a function call called free. And when we say free, it's going to, for example, take this block and tell the operating system, hey, this block of memory is not being used anymore. And then later on, when we call malloc, we might get back this same block of memory, and we might use that to insert a new number. So when we delete something, even though, you know, that block is still sitting there on paper, that memory, if we free it, is available for reuse down the road. And so we're not sort of, you know, continuing to waste more and more memory each time we delete. As long as we call this free function, these blocks will be available to be reused. All right, so let's go back and look at inserting and deleting at the beginning of a list. And I'm going to simplify my linked list now and just show, you know, my numbers with arrows, but they're really, you know, complex blocks that have a number and an address of the next thing. But I'm just going to draw this, you know, more succinctly as just, you know, numbers pointing to numbers. And, you know, if I want to insert a 5, this will point to a 5, 5 will point to 7. But let's say I want to insert a 1. Well, you know, technically it's easy. I make a 1 and I have that point to the 2. The problem is this notion of, you know, where did my list begin has now changed. My list used to begin right here. So maybe I had a variable that pointed to that too. Well, unless I change that variable, I'm no longer pointing to the beginning of the list because now my list begins right here. So every piece of my program that refers to the beginning of the list now has to refer to a different location. Has to refer to where this 1 is stored.
It's not like a kind of a weird idea, but would it be stored kind of 4 less on the location memory? As if you're going backward instead of like adding 4 every time, subtracting 4?
Can you say that again?
I like going backwards in memory. Instead of skip time by 4, 4A, C, you go back and go like 100, and then not super familiar with hexadecimals, but it'd be like 096 if it was in base 10.
Mm-hmm.
That's kind of the idea. So that's kind of where you figure out where in memory your list would be, the list will start.
Okay, so yeah, you might be able to go backwards, and from the old start and get to the new start, but we get into more trouble if we try to delete. So if I want to delete the 1, for example, right, I can go back to referring to this as, you know, the start of the list. If I delete the 2 And I think that my list begins right here. I'm probably going to get a segfault. I need to take my notion of where the list begins and change it to be right here. And you know, if I insert a 25, that 25 might end up right here. And this 20 will point to the 25. And the 25 will point to the 30. And if I still think my list begins right here, I've got a really odd view of my list now, because I think my list contains a 25 followed by a 30. I need to update where my list begins and say, no, my list begins here now. So when I look at my list, I see a 3, a 7, a 20, a 25, and a 30. So with the way we've described this so far, we have this potential for needing to change where the list begins, based on whether we insert or we delete. And that's not impossible to do, but it's a bit of an edge case. And so we're going to manage that with a little bit of a trick, and this trick is called a sentinel node. And the sentinel node is really just kind of a placeholder. So let's say I have a list containing a 2 and a 3 and a 5 and a 20 and a 30. I'm going to always have a special node in the beginning that I call my sentinel, and the sentinel's only job is to point to the first node. And when I want to refer to my list, it's the address of the sentinel that I'm going to use. This is like the handle to my list. It's the thing you use to get a hold of your list, to pass it to a function, to pick it up and look at it and explore it and manipulate it, right? It's the thing we use to get to the list. This does not actually have a piece of data that's part of our list, though. Its only job is to point to the first thing in the list. So now if we want to insert something in the beginning of the list, if we want to insert a 1, we can do exactly what we've been doing as if we inserted a 4, for example. We make a new node 1, we change it to point to the thing that should come after it, and we take the node before it, which is the sentinel, and we say, hey, point to the 1. And our handle to the list hasn't changed. The address that we use for getting to the beginning of the list is always the address of this sentinel. But when we look for the data in our list, we don't look at the data here. We say, hey, let's look at where the sentinel points. That's the first thing in the list. It's a 1. And that points to the next thing, a 2. The next thing is a 3. And now if I want to delete the 1, I just change the sentinel to point where the 1 is pointing. Goes like that. And now what's our list look like? Well, the sentinel points to a 2. That's the first thing in the list. That points to a 3 and a 5. And if I want to delete the 2, well, the 2 is pointing to the 3. I'm just going to change my sentinel to point to the 3. I've just deleted the 2. So the sentinel points to the first thing in the list, which is a 3, and then a 5, a 20, and a 30. So that's a trick we're going to use. And we're going to use that in PA1. And it's going to simplify our programming. It's going to mean that once we know the address in memory where our list is stored, we never have to modify that. We're going to set it up once in the beginning of our program. It's going to be the same for the rest of the program, even if we insert things in the beginning of the list. This also helps with the idea of when you delete everything from the list. Because if I delete the 3 and the 5 and the 20 and the 30, all I got to do is have the sentinel point to null. And when I try to find the data in my list, I'll look at the sentinel and say, well, the first thing in my list is stored at location 0. Oh, that's not a valid location. I guess there's nothing in the list. Alright, is this making sense so far?
Yeah, I try to think of using null, has a node point to null as a way to change with nothing in an array. As like a way of, you know, cause I was doing a little test, I was checking out the test program, and when there's nothing to list, it will say not found or anything like that. So I imagine the way to check for that is just using this method a point and null for that.
Mm-hmm.
If that's the right way to think about it.
Yeah, and it's not actually a special case. When we want to search for something, we'll always start with what the sentinel points to, and we'll keep searching for nodes. And if we run out of nodes and we don't find it, then we can say it's not in the list. If our list happens to be empty, the same algorithm will work exactly. We're not even going to need to do a special case. But yeah, that's effectively what's happening. So let's do one more example of this with a memory map, but let's have a sentinel node this time. And let's see what happens. And again, this is not what your memory actually looks like, but you know, it's a convenient example. All right, so let's have our sentinel stored at, I don't know, it doesn't have to be stored at the beginning. Well, let's just suppose our sentinel is location 100. Right, so this is our sentinel node. And when we begin our program and we want to represent an empty list, we're going to say, hey, the thing after the sentinel is null. There's nothing else in the list. That's an empty list. So let's insert the number 10. So we'll call malloc, which will say, hey, give me enough memory to store a number and a pointer to another node. And let's just suppose, you know, it gives us the location 104. We need more than 4 bytes, but don't worry about that. Let's suppose it gives us the location 104. Okay, we're going to store a 10 here. And that's going to be the last thing in the list, so it's going to point to null. The sentinel is going to point to that first node, so this is going to change to a 104. So what we've got now is our sentinel pointing to 10, and the 10 points to null. I'm not going to draw an arrow. I'm just going to leave it, you know, with nothing on there to mean it's pointing to null. So now let's insert a 20. So we'll find a new location in memory. Let's say it's this location 108. There's a 20. It's going to get inserted after the 10. So we know this is the last thing in the list. This is going to point to null. But the thing right before it, 10, is going to point to this 20. So this will change to a 108. So our sentinel points to location 108, which has the 10. That node points to location, points to 104, which is a 10. That node points to location 108, which is a 20. And 20 points to null, so that's the end of the list. Now let's insert a 15. So we'll put a 15 here. Well, we'll search through. We'll start with our sentinel points to 10. 10 is too small. That points to 20. 20 is too big. So we want to insert before this and after this previous node. So we'll have our new node point where the previous node points, that's 108, and we'll have the previous node point to our new node, that's 10C. So now our sentinel points to 104, that's a 10, that's our first node. That points to 10C, which is a 15, that's our next node, and 15 points to 108, that's a 20, and 20 is the last thing in the list.
I do have a question. You said that each of these inserts are actually in a random location memory, because the one you're illustrating is just a fictional type illustration, right?
Mm-hmm.
How will you know where it is located in memory? Like, do we have to check every time whenever we do insert, to know exactly where it's located?
So when we want to insert a number, we're going to call the malloc function, and malloc will give us, you know, 110, 114, some location in memory to use. And we're going to store that location in the previous node's information. So the previous node's going to remember where we inserted the node that comes after it. And that's where we're going to use when we want to find that next node. We're going to look in the information stored with that previous number. So we're going to have to save it. And we're going to need our memory to have something more than just these integers. It's going to have to be a pair of things, an integer and a pointer to another node. And so we're going to make a structure, using a C structure statement, and it's going to have these two pieces to it.
I have a question.
Yeah.
Is the sentinel node there just so that if we change the first number,
Mm-hmm.
we're actually kind of changing the second number?
Exactly.
Okay.
So let's delete 10. So we'll start at the sentinel that points to a 10. That's the thing we want to delete. So now, this is the node we're deleting. The sentinel is the previous node. So we're just going to change the previous node to point to where the node we're deleting points. The node we're deleting points to 10C. We'll change the previous node to point to 10C. And now the sentinel points to 15. 15 points to 20. Bingo, we've just removed the 10. But our sentinel is still at location 100. So yeah, exactly what you said. We're putting in the sentinel so that if we want to delete the first thing, we're actually deleting the second thing. And if we want to insert before the first thing, we're actually inserting before the second thing. And the first thing never changes. So we can write some pseudocode now if we want to insert n into our list. Start at the sentinel. Follow the links. We're always going to follow the links. We're always going to begin with a sentinel. We're going to see where that points. We're going to see where that points, and so on. We're going to follow the links until we find a number bigger than n. And at this point, we want to insert between that node and the previous node. So if we want to insert a 15, start at the sentinel, follow it to a 2, a 3, a 10, a 20. Stop as soon as you find a number bigger than what you're inserting. And now we want to insert between that node and the previous node we were at. So we're going to need to remember where that previous node is. Once we know the two nodes we're inserting between, then we make a new node. We have it point where the previous node is pointing, and we have the previous point to our current node. So let's make a new node called new. Have new point to wherever the previous node is pointing. And have the previous node point to new. All right, let's do a 5-minute break, and we will come back, and I want to look at programming assignment 1. So we'll go through the description of it. We'll run the sample code, and then we'll start looking at code that we can use to create these linked lists in a C program. So let's come back at, let's see, it's 1:05. Come back in a little over 5 minutes. All right, so I'll see you back here then.
So we're gonna jump the car, try to get it back to the driveway, and then just, he's gonna go home and not try to deal with it today, because he's feeling bad. I told him we could just try to jump it and get it back. He said, no, he thinks that we need the heavy duty jumpers he has.
Get it back out of here.
True. And he's not gonna come in because of, symptoms. And, he is out of money and ideas. So I'm like, yeah, we'll just talk about it later when we have a chance to talk about it and stuff. So, yeah. So that's the update. Hello? Hi. Oh, really? Oh. Oh, fantastic. Okay.
Alrighty, welcome back.
Oh,
Hello. All right, let's take a first pass through the posted programming assignment, and then we'll start looking at some coding details. And we can't discuss all the nuances of PA1 yet because, you know, a lot of them relate to how we're going to implement it. But let's at least get a first pass through and look at the sample code. So program. Go ahead.
So are we setting up a Git repository for CSE222 like we did for 224?
No, so we're not using Git at all for this course. You can continue to use it on your own, of course, but all your submissions are going to be made through Canvas as a tar file. So no Git submissions this time.
Okay.
All right. All right, so we're going to create a linked list. We're going to write a series of functions for interacting with linked lists, and then you're going to write a main program to allow a user to manipulate a linked list from a series of typed commands. So the basic nodes are going to need to be, you know, more complex than just integers. They're going to have an integer piece, but also a piece that points to another node. And we're going to do that by using a structure statement in C, and we're going to create a thing called a mynode. And a mynode is going to contain two pieces. It's going to contain an integer called data, and it's going to contain another piece called next node, which is a pointer to a struct mynode. It feels self-referential, but it actually works. So this is the structure you're going to want to use. You're going to want a structure called mynode, and you need to pay attention to uppercase, lowercase very carefully. Mynode with an uppercase N. This is something called camel case. We'll do this a lot in 223. Camel case is a way to, you know, sort of have multiple words in variable names or structure names, and break it up into individual words by using uppercase, lowercase changes. You can do this with underscores. That's called snake case. Or you can just jam everything together. That's just called confusing. So the next node is called next node, right, with an uppercase N here. And that's a pointer to a struct mynode. This whole thing is a struct mynode. So a mynode contains an integer data and a pointer to another thing like itself. So what is a struct mynode? It's one of these boxes. That's the data piece. This is the next node piece, which is a pointer to a struct mynode. In other words, it's a location in memory. It's a number that corresponds to a memory address at which we would find another one of these structures containing an integer piece of data and an address at which we would find another one of these nodes. Or at which we might find, nothing, because it's not actually an address. It's this magic address called null, which is a 0. So that's going to be the basic structure for each of our nodes in our linked list. It's a thing called a mynode. It's got a data and it's got a next node. And next node is null when you reach the end of the list. All right, you're going to want to keep track of a sentinel node. Your sentinel node should be called mylist, and your mylist is simply a pointer to a struct mynode. So in your main program, you're going to declare a variable called struct mynode star mylist, and that's the address in memory where your sentinel is stored. It's a pointer to a struct node. It's a pointer to one of these boxes. So that's the basic structure. And your goal is to create a series of functions. Your first goal is to create a series of functions for doing these algorithms that we've been doing on paper for inserting, deleting, searching, and so on. So you're going to implement the following functions. You're going to make a function called init. And I'm showing you the prototypes for each of these functions in here. So init doesn't take any arguments, and it returns a pointer to a struct mynode. What init does is create a sentinel node. And that's its only job. It creates a sentinel node for an empty list. So when you call the init function, what your code should do is, call malloc to create, to find enough memory to store a struct mynode. Set the next field to be null, to say, hey, there's nothing after the sentinel, so it's an empty list. And there's a special instruction here. The data field of the sentinel should be set to 1, 2, 3, 4, 5, 6, 7. That's just a flag. That's just so that we know if we try to print our list and we happen to see a 1, 2, 3, 4, 5, 6, 7, we know we did something wrong. We're printing the value of the sentinel, which we shouldn't be doing. So this is what an empty list is going to look like. It's not truly empty. There is a sentinel node, because there's always a sentinel node, but the sentinel points to null, which means there's nothing after the sentinel. That's why it's an empty list. And we're setting the data field of this to 1, 2, 3, 4, 5, 6, 7. Why? Just because that's what it says to do. Alright, so that's your init function. The add function should take this sentinel node, so it should take the address where the sentinel is stored, and it should take an integer number that you want to add to your list. And when you're done, you should have created, a new block with that number in it and adjusted pointers in the list so that that new block is now part of the list and the list is still sorted. Right, so the list should always remain sorted, smallest to largest, so that when you insert in the proper place, the list remains sorted. And this function should generally return a 1, saying I succeeded in inserting your number. The only time you would return a 0 is if there's no memory left on your machine. That's usually not going to happen. But when we look for a new spot to store our number, right, when we did this on paper, we said, okay, we can store something at location 110. When we do this in C code, we're going to use the malloc function. And we're going to say, hey, malloc, tell me where I can store a new node. There's a possibility malloc will say, sorry, there's no memory left. Okay, in that case only, the add function should return a 0, saying, hey, there wasn't enough memory left to make a new node. That's not going to happen. And I'm not going to test that because I would have to fill up all the memory on my machine to do that. But put the code in there anyway to make sure that the malloc succeeded and the add succeeded. Alright, there's a print function. Print takes the sentinel node and nothing else. All it needs is a sentinel. Alright, the handle to the list. And what the print function does is it prints out the contents of the list. So it prints the numbers, the data pieces, starting with the first node, not the sentinel. So it should not print out 1, 2, 3, 4, 5, 6, 7. But if this points to a node with a data of like 2, then the first number that's printed out should be 2. And so this should print out all the nodes separated by spaces on one line. So don't print new lines after them, but print a new line at the end of the whole list. Alright, delete is just like insert. You give it a list and you give it a number, and it will remove that number from the list if it finds it. If you try to delete a number that's not in a list, then delete should notice that and it should return a 0. If it succeeds in deleting, it should return a 1. And then search looks for a number in the list and it returns a 1 if the number is found, a 0 if it's not found, but it does not change the list. And then one more function called cleanup. And cleanup, you give it the sentinel node and it basically frees all the memory that's been allocated. So if I have a list where my sentinel points to a 2 and that points to a 5 and that points to a 10, it should release all of the memory being used to store those nodes, including the memory used to store the sentinel. And we'll talk more about that another day, but this is related to what are called memory leaks. A memory leak is when you run a program and it allocates memory by calling malloc, but it doesn't eventually free that memory. So memory gets allocated, and even if you're not using it anymore, like if you're exiting your program, if you don't free that memory, that's called a memory leak. And in some cases, that can degrade the performance of your system over time. In Linux, it won't. Linux will automatically free the memory when your program exits. But for good programming practice, we want to make sure we don't have memory leaks. So we're going to want to free all of the memory when we're done using it, and that's what this cleanup function will do. So you give it the address of the sentinel node, and it will go through and release all the memory. And these are all the functions that your main program should use for interacting with a linked list. Now you can write other functions in your main program for, processing input and parsing and all this kind of stuff. But the interface between the main program and the linked list is just through these functions. And that's it. So your main program should never, check to see if the next field of a node is null. That's not in the domain of the main program. That's what these things are going to do. And so here's a concept called an abstract data type, or an ADT. And the idea is we want firewalls. Here's our main program. Here's our linked list code. So here's the C code that, starts at the beginning of a list and follows links and finds the node you should insert before and adjust the pointers and so on and so forth. And there's a wall between these. And the way that you interact between your main program and this implementation is very, very tightly controlled. In our case, it's controlled because you only do that interaction through these functions, nothing else. And this is a very standard way to implement data structures. And when we get to object-oriented programming, right, this is the whole idea of creating classes, which we'll talk about, in spring. But the objects that we use in object-oriented programming are instances of classes, and the idea of classes is to be able to establish and maintain this very precise control between how, say, a main program interacts with the implementation of a data structure. So your linked list implementation code, your insert routine, your delete routine, will be doing very low-level things with memory. It'll be doing mallocs and frees and following pointers and things like that. Main program never does anything like that. Anytime the main program wants to interact with a linked list, it does it through one of these functions. And that's super, super critical. it's critical because, for example, if you were using a commercial linked list package and it got updated and they changed the way that some of these routines were implemented, right, your interface to the linked list would still be the same. It would be unchanging. If you want to add something, you use the sentinel node and the number you want to add, and you get back a 0 or a 1. And whether this is being implemented, you know, using these little boxes with 2 pieces, or a two-way list where we have pointers going backwards, or it's sending text messages to someone on a desert island who's writing your nodes in the sand and keeping track of it, none of that would change your main program. Right? Your main program is only going to interface with the linked list through these methods, these functions. So this is the idea of an abstract data type. And we'll come back to talk about this more later in this course, and then a lot more in 223. But part of how I'm going to grade your assignment is I'm going to write my own main program and link it with your implementation of these functions. And so if you call your cleanup function something else, when I try to link my code to it and I try to make a call to cleanup, it's not even going to finish compiling. If you decide that your add function is going to return a 2 if it's successful and a 1 if it's out of memory, when I write my code and I link it to your add function, it's not going to work. So you want to get some practice with really following specification like this. And this is very typical workplace experience, right? You're asked to implement a set of functions. You're told what the prototypes are, what they take, what they return, what they do, what the side effects are, and so on and so forth. So this is why I'm going to be a stickler and say, you know, this has got to be a my node with an uppercase N. It's got to take no arguments. This has got to be called init, all lowercase, and so on and so forth. All right, so we'll talk more about ADTs as we go throughout the course. Each element in the linked list is something containing 2 pieces, a data field and a next node field. So that's the 2 pieces of that block that we keep talking about. And here's a rehash of the algorithm we were using to insert things, right? To add a new number to the list. Create a new node with a desired data value. Search the list for the proper point to insert. In other words, find the first number that's too big. Adjust the previous node or the prior node's next field to point to that new node, and adjust the new node's next node field to point to the node that should come after it. This should say next node. All right. To delete, to search, to print, we do exactly the same thing. All right, you're going to use malloc to find space for a new node. And how many bytes do you need for a node? Well, you need enough bytes to store an integer and a memory address. Well, an integer is usually 4 bytes, but it could be 2 depending on what machine you're on. A memory address could be 4 bytes, could be 8 bytes, could be more. It depends on your operating system. So we don't want to do this calculation ourselves. So we're going to use the size of directive and say, hey, figure out the size of a structure my node. And the compiler will say, okay, a my node has an integer and it has a pointer to memory, and these are the ways that things get packed, and this is how the loader will organize these and so on, and it will probably say, okay, you need 16 bytes. Right? But it will make that decision, and so when you malloc space for a new node, malloc size of struct my node, and it's not struct star my node. We're trying to allocate enough space for an entire node, not for a pointer to a node. And when you're done with memory, if you're either deleting a node or if you're calling this cleanup function, you want to use the free function call to release the memory. All right, so main program. This is a rehash of what I was saying. It's important the main program never directly manipulates the data structure. Everything should be done through the above routines. So main can call any and all of these functions, but it shouldn't do anything lower level than that. And so your main program basically begins by printing out a prompt, so just a greater than sign, and it waits for the user to type a command. And there's a number of commands the user can type. They can say I space followed by an integer, and that will insert the number into the list. They can say P, which will print the list, all on one line with spaces in between. They can say S number to search for a number. They can say D number to delete a number. They can say X to exit the program, which should release all memory. Anything else should give them a help message showing them what the legal commands are. And there's a sample executable on the server. So let's hop into that. And so we can run /temp/pa1 sample. So it prints out a prompt. And if I, type an unknown command, it should give me some kind of help message. So here's a synopsis of the things that I can do. So I can say, okay, let's insert the number 10, let's insert 20, let's insert 30, let's insert 5. And now I can say P, let's see what the list looks like. And I can see the numbers I inserted, but they're in order, 5, 10, 20, 30. I can insert a -10, I can insert a 2000. And if I print, there's what my list looks like. I can search for a 20, that's found. I can search for a 21, it's not found. I should be able to search for something before the first element. I should be able to search for something after the last element. Those are edge cases to test. And if I don't type an integer, that's an error. If I type something that's not an integer, that's an error. If I type insert haha, that's an error. If I search for haha, that's an error. So do all the usual syntax checking, parsing and processing from 224, right? And this is all stuff you can work on without knowing anything about linked lists. You can wire up the main program to do all of the input processing, parsing, and so on and so forth. And I can delete, so I can delete the 20, and the 20 is gone. Make sure you can delete the first thing in the list. Make sure you can delete the last thing in the list. Make sure after you delete something, it's actually deleted. If you delete something that was never found, it should give you an error message, and so on. If you insert something that's already in the list, it should catch that and say the node's already in the list. So before you call your add function to insert, call search. See if the number that the person's trying to insert is already in there. If it is, give them an error message. And then when you're done, you can just hit an X, and that should exit the program. All right, coding styles. So you need to use some kind of consistent coding style, which means I want you to indent based on levels of nesting, conditional statements, loops, functions. All of these things should be indented. You can pick your own indenting style. If you look at that second text that I posted on Canvas, it's got a whole chapter on coding style that talks about, different indent options, why we're indenting, and so on and so forth. But you need to have some kind of consistent indenting style, which you're hopefully developing, as you go through your coding courses and such. You need to comment your code thoroughly, right? Particularly in this course, it's not unreasonable to expect every line of code to have a meaningful comment. Because we're doing, some pretty significant manipulation of data in these algorithms. And you want to explain why you're doing something. If you say, I equals next, don't put a comment saying set I equal to next. That's obvious from looking at the statement, I equals next. Why are you setting I equal to next? Change I to point to the next node. Well, that's a better comment, right? That says why I'm doing this. So think about, meaningful comments throughout your code. I also want to block a comments in the beginning of each function, telling me what the function does, what the arguments to it are, what the output is, what does it return, what are the side effects, what are the special things that you should be aware of. And so a hint here, if you're writing an add function, saying adds a node to a list is not sufficient commenting. If I was writing an add function, I might say something like, and don't just take this, right? Insert the number into the given list. the number will be inserted in the proper place to keep the list sorted from smallest to largest. If the list is empty, a single node will be added to it. The argument list points to a sentinel node which never changes. This function returns 1 if it's successful, 0 if it runs out of memory. Right? So document, right? And think of it from the perspective of, 2 years from now, you want to go back to this code and understand it. Right? What do you have to describe in the code to make that more possible? All right. I also need a block of comments in the beginning of the program, which lists your name, the date, the course number, and a detailed description of the program. Right? And again, linked list program or programming assignment 1 or program to play with linked lists is not a sufficient level of detail. Tell me what you can do with this program. Right? All right. You're also graded on how you structure your program. So your program should have exactly 4 parts to it. Main.c, which is your main program, and any other functions related to your main program. If you have a separate function for parsing input, and so on and so forth. All of that goes in main.c. Functions.c is a single file containing these 6 functions and any other functions that are used by these. So if I'm going to write a function called, new node or something like that, put that inside functions.c. And basically, when I have my own main program, I'm going to link my main program to your functions.c. All right, main.h is an include file, and it should contain the following. It should contain the definition of a struct mynode, and it should also include prototypes for all the functions inside your functions.c. And then a make file, which builds an executable out of those 3 pieces. And this should be a proper make file in the sense of CSE222A. It should only compile things that are necessary to compile. So if you change one file and you say make, it shouldn't recompile every file. It should compile things to objects, which are .o files, and then link those objects together into an executable. And it has to include a clean option, which gets rid of the objects and gets rid of the main program. All right, those 4 pieces get turned into a tar file. Here's a good tar command you can use, tar cvf pa1.tar, and then the names of the 4 pieces. When you do this, this will create a file, pa1.tar. And that's the file that you're going to upload to Canvas. And figure this out before you've got your code finished. And figure this out with junk files. Make yourself, just kind of a placeholder, main.c, functions.c, and so on, and turn it into a pa1.tar. Copy that to another directory, untar it. Make sure you can do that. Don't try to learn tar the morning that you're submitting the assignment, because it's really easy if you use tar the wrong way to corrupt your files. And if you don't have good backups, then you've lost your work, right? So figure out how to use tar, come to office hours, go back and look at the how-to, look at your 224 notes, and so on. And when you're ready to upload, right, save all your files as pa1.tar uploaded to Canvas. PA1 on Canvas has an upload button, and it will only accept files of type .tar. You can also only upload once. So once you upload whatever version you uploaded first, that's what I'm going to grade. So make sure you're uploading the correct file. Make sure pa1.tar is correct. And one way to do that is, go into another directory, copy pa1.tar into there, untar it, execute the make command, run all of your test cases on main. So that's what this suggestion is here. If you haven't done this before, right, if you're working on the Linux server, linuxengrcs.com, you're building your files there, you're testing them, you're making your tar file, you've got a tar file sitting on the server, how do you upload that to Canvas? Well, you have to download it to your PC. You can do that with SFTP if you're running Linux. You can do that with WinSCP, which is like PuTTY if you're on Windows. If you're on OS X, you can do SFTP. And there's verbiage about this in the how-to guide also. But we've done this in 224 also. All right, final comments, grading. So, deductions, right? If you don't submit, if your tar file is corrupted, if you're missing files, if there's no main.h and I can't, you know, run your program, it's 100% deduction, right? You basically get a 0. If your code will not compile, or it will not run, it compiles, but when I try to run it, it immediately says segfault or something like that, you're down 50% automatically. If it's an easy fix that I can make, I'll fix it and I'll continue grading. But that's going to depend on how well the code is commented, how well it's organized, and how easy the bug is to find. If it's something like, you know, you put a comment in the beginning, but you used a single slash instead of 2, that's going to be easy for me to notice and fix. So I'll probably go ahead and do that, and I'll build your program and continue grading it. But if it's not something pretty straightforward, it's going to end up being a 0. Is it possible to push the tar file to GitHub and then download it onto your machine from there? Yeah, you can do that. But be really certain that you've got the right tar file. So WinSCP, if you're running Windows, WinSCP is probably a safer way to do that, because WinSCP basically gives you a pair of windows, one on the server, one on your local machine, and there's less chance of getting confused about, you know, if you have multiple pa1.tars kicking around, that might be a little more straightforward. All right, if you don't follow the description of exactly how things should be named, what they should be called, the prototypes or the functions, the structure pieces, and so on and so forth, that's going to dock you 50%. Because basically I can't test my code until I go in and I do a lot of editing on your code, or I change my main program to fit your specification. So that's really important that you follow that. And if you don't split it into the pieces that I've described, main.c, functions.c, main.h in a make file, that's going to cost you 35%. All right, assuming you've got those things in place, and I can run your program and I can test it, you get points for the following. If you have a proper make file, that's 5%. If your init, print, and search functions work correctly and are implemented using the algorithms we're going over in class, that's 10% each. Add and delete get you 14% each, because those are slightly harder than init, print, and search. Your main program gets you 10%. And the main program is big. The main program is going to be bigger than the code for the linked list, but it's a rehash of 224. So hopefully that's not going to be a big investment of effort. If you have no memory leaks or errors or warnings from valgrind, and we'll talk about valgrind in a bit, that gets you 10%. If I can compile just by saying, you know, the default GCC command in your make file, and there's no warnings or errors, then you get 5%. If you use GCC with switches that say, you know, suppress these kinds of warning messages, and I try to compile without that switch and you get warnings, you're going to lose points for that. So definitely in this course, pay attention to warnings. And that's worth noting in big text. In 224, if you got warnings, you know, I said that might be bad, but you might get away with it. In 222, any warnings you get are going to come back and hurt, right? Almost guaranteed. If GCC complains about something, even if it's willing to compile it, if it's complaining about something, it's setting up one of these landmines that's probably going to come back and bite you later. So definitely pay attention to those. All right, and then 12% for the various commenting and coding style considerations.
If you delete an item from the list, do you have to free that item?
Yeah, definitely.
Okay.
And so this business of no memory leaks. So there's a command called valgrind. And if you want to use valgrind, basically instead of just saying, you know, PA1 sample, say valgrind and then the name of a program. And it looks exactly the same as if you just run your program, except you get some extra information in the beginning and you'll get a lot of extra information at the end. So I'll insert a 10 and I'll insert a 20 and I'll print my list and I'll delete my 10 and I'll insert a -10 and I'll insert another 10. And that's all looking great. Okay, I'm going to do an X to exit my program. After my program exits, valgrind will print additional information. And so it's saying heap summary, in use at exit 0 bytes 0 blocks. Total heap usage 7 allocates 7 frees. It's telling me that I called malloc 7 times basically. But I also called free 7 times. And even though I allocated a total of over 2,000 bytes of memory, at the end all of that memory was released. Here's what you're looking for. All heap blocks were freed, no leaks are possible. And at the end, error summary, 0 errors. That's what you need to get those points. And if you're doing something slightly off, if you're forgetting to initialize a pointer to null, if you're using something that you haven't allocated correctly, if you've forgotten to freeze something, malloc will yell at you. It will yell really, really loudly. And that's good, right? You want a program that can yell at you when there's something off in the program, so that you can go into the program and you can figure out what it is and you can fix it. And then when malloc is happy, when it's saying all heap blocks were freed, no leaks are possible, error summary 0 errors, malloc's happy, I'll be happy. So yeah, it's a really, really useful program. It's kind of magical actually. Alright, so that's the memory leak business. And every class that you take where you're doing any kind of C programming, when you get to a university and you're doing C programming classes, right, you're going to have to deal with memory allocation and freeing memory. And there's classes where, you know, if you have a single memory leak, you get a 0 on the assignment. And you might spend, you know, 3 weeks writing 1,000 lines of code, and you got one memory leak, and you get a 0. And that's like kind of horrifying. So this is a good place to get in the practice of checking for memory leaks and getting really good at resolving them. And you know, it only costs you 10 points here. But get in that habit, and then when the stakes are higher, it won't be an issue. And memory leaks are a big bugaboo, right? So there was an early version of Firefox when it first came out that if you ran Firefox on your PC and you didn't close it, your system started running slower and slower over the next few days. And eventually your system would just be totally bogged down. It would be like crawling. Everything would take forever to do anything. And as soon as you closed Firefox, boom, everything came back to life. And there were memory leaks in there. And the longer that your program was sitting there running, even if it wasn't doing anything, the longer it was running, the more memory it was sucking up. And eventually your machine was just running out of memory. And by exiting the program, the operating system went back and reclaimed all of that memory. So that was my first like direct exposure to the horror of memory leaks. But this still happens. And you know, with programs that don't exit, for example, if you're running a web server, the web server never really exits, right? It runs as long as the server is booted up and continuing to run. And so if there's, you know, just something that leaks a few bytes of memory every now and then, after enough time, your system's out of memory. And it's a performance killer. All right, so other questions? All right, so let's look at coding this stuff. Coding. So let me make another disclaimer here. We're going to write a lot of code in this class during lecture, and I'm going to write a lot of code or pieces of code on paper. And generally, what I'm writing will not be directly usable in your programming assignments. So for example, I'm going to call this main program main1.c. You've got to call your main program main.c. Okay? I'm going to define a structure called node, but you've got to call your structure mynode. Okay? So I'm doing example code, but I'm reserving the right, and in fact I'm intentionally doing things differently from how you might have to do them on the programming assignments. Alright, so you need to be able to adapt, and that's useful. Alright, so I'm going to make a program called main1.c. And I'm going to make a structure. Let's make a structure for a linked list node. So I'm going to say struct node. I'll have an integer piece called data. And I'll have a next piece called next. And I'll end it with a semicolon. Alright, so there's a definition of a structure. Alright, so I'm going to start my main program. I'm not going to take any arguments. I'm just going to build some nodes and do some stuff with them. Alright, so I'm going to start off with a struct node called a sentinel. This will be the handle to my list. So I'm going to call malloc and I'm going to say, hey, I need some memory. I need memory that's big enough to hold a struct node. And malloc's going to give me an address, and I'm going to set sentinel equal to that address. So sentinel is the address of a node. And if I like, I can think of it as sentinel points to a node. This is this business of, having to draw pictures and find a way to represent this that makes sense to you. So I'm thinking of sentinel as a pointer to a node, something that points to a node. It's actually, it's going to be a pointer. It's going to have an address in it. It's a pointer to a struct node. But at some point along the way, I'm going to actually start thinking of sentinel as one of these little rectangles with two pieces to it. And it's not. It's really a pointer to one of those. But at some point along the path of working with linked lists and pointers and structs and so on, you may find that you've made this leap to where you're actually thinking of these pointers as actually being the things themselves. And that's okay. Just be aware that those are slightly different things, and it will probably get confusing as it's getting clearer. So this stuff is not, what does I++ mean? And someone tells you, and you say, okay, I got it, right? The concepts we're working with in here will be confusing, and they'll start to make sense, then they'll get confusing again, and then they'll make perfect sense, and then they'll make no sense, and it's kind of a back and forth thing. But eventually they will make perfect sense, hopefully. Alright, so I'm going to say sentinel equals malloc. So sentinel is now the address of a node. And so let me draw a picture. And I want to set a magic number up here in the data field, and I want to set null down here in the next field. So let's set the data field to 1, 2, 3, 4, 5, 6, 7. All right. When we have a structure, we can get to a piece of the structure by saying structure name period and the name of the field. Data like this. But there's one trick here, right? Sentinel is not a struct node. Sentinel is a pointer to a struct node. Right? Sentinel's not a struct node, it's a pointer to a struct node. If you have something that points to an integer, and you want to actually get to the integer, you want to dereference that pointer, we say star followed by the name of the pointer. So if we say star sentinel dot data equals 1, 2, 3, 4, 5, 6, 7, so this, the star sentinel, says go to the node that's pointed to by the sentinel, and then set its data field to this magic value. And similarly, I can say star sentinel.next equals null. Alright, so let's see what this does. So I'll compile it with a G switch for GDB, debugging. I'll call the output. And I don't have my malloc function because I need to include standard lib.h to get malloc. So now I can run main1, and I can start it. And the first thing I'm going to do is I'm going to call malloc and set sentinel equal to whatever malloc gives me back. Well, if I print sentinel right now, it's a 0. But if I execute this call to malloc and now I print sentinel, sentinel's equal to a nice memory address. It starts with a bunch of 5s. This is a thing on the heap. And if I examine what's at this memory location, it's got a 0. It's got a bunch of zeros. But now I'm going to say star sentinel.data equals 1, 2, 3, 4, 5, 6, 7. And now if I examine this memory location, hey, it's got a number in there. What's this? Well, this is 1, 2, 3, 4, 5, 6, 7 in hex. And now I'm going to say star sentinel.next equal to null. And that's not going to change anything because null is a 0, so it's probably stored as 0 somewhere in here. And now I'm going to return, and that's it. I'm done. And if I just run this program from the command line, it doesn't seem to do anything. It actually allocated some memory. It set a field equal to a number. It set another field equal to null. But there's no visible effect to that. But if I run this through valgrind, it runs, but guess what? Leak summary. Definitely lost, 0 bytes. Indirectly lost, possibly lost. Still reachable, 16 bytes in one block. Right? So I have a memory leak. In use at exit, 16 bytes in one block. Well, why do I have a memory leak? Because I did a malloc statement right here, and I never did a free. So my program allocated memory, and then I exited without freeing that memory. If I wanted to get rid of that leak, I can just say free sentinel. And now if I run this through valgrind, it tells me all heap blocks were freed, no leaks are possible. It tells me I did one malloc and I did one free. Alright, but that's not terribly interesting right now because we haven't really done anything with this sentinel node. So let's make a second node. So let's make a new node called new. It's going to be a pointer to a struct node. We're going to call malloc to find a place to store it. We're going to tell malloc to give us enough memory to store a struct node. And so new is going to be a new block. And so I'm going to think of it like this. Here's new, and it's got two things to it. So I'm going to set the data field of this new block to be 42. So I'll store a 42 here. I'll set the next field to be null. So this will be null. But I want to set my sentinel to point to this new node. Now I'm doing this all, just kind of barehanded. This is piecing things together by hand. Eventually we're going to write algorithms that will do this for us inside an add function and so on. But we're just playing with this, putting it together. Let's see. How can you declare the struct node sentinel before it has a memory address? So we can declare this to be a pointer. We can declare this to be a pointer. And if we tried to use it, we'd get a seg fault. But all we're doing is making the declaration. It's like saying integer star I. I is a pointer to an integer. That's legal, but before we do anything with I, we would want to make sure it points somewhere valid. So here we're declaring this to be a pointer, and here we're giving it a value. Here we're declaring new to be a pointer, and we're giving it a value in the same statement. But it's the same thing as first declaring it and then having an assignment statement. Alright, so let's have the sentinel point to our new node. So I want to build a little list by hand like this. And so the next field of the sentinel looks like this. Right, the thing sentinel points to is a little block. Take the next field, and let's just set that equal to new. So let's run this. So I'll start off with the sentinel. I'll set the data field to that. I'll set the data next field to null. I'll make a new node. I'll set its data field to 42. I'll set its next field to null. And now I'm going to set sentinel's next field to point to new. So let's print out what sentinel is. Well, sentinel is a location in memory. If I examine that location, I find 1, 2, 3, 4, 5, 6, 7. And I also find a memory address, 5555, 5575, 6280. And if I examine this memory address, I find a 2A. What's 2A? That's the hex value of 42. That's my new node. So I've actually set up this structure. I had a sentinel with this data field, a next field that had an address, and at that address I find my new node with a value of 42. And if I look at the next bytes for the next address, it's all zeros. That's what these zeros are right in here. Now we can do this in GDB. let's add one more node to our list. Let's make another node, and let's put a 100 in there. Let's call this newer. So I'll make a new node called newer with 100 in it. I want new to point to newer, and then I want newer to be the last node in the list. So let's make another new node. So let's make newer. We'll have newer's data be 100. We'll have newer's next be null. And we'll have our new node point to our newer node. So new next should be newer. And I'll post this code on Canvas after class. So all we're doing is we're manually constructing these blocks and manually manipulating the pointers to have each block point to the next block and so on. When you examine, someone asked about GDB's memory command. When you examine with the X command, you can add a lot of switches to it. You can say I want to look at, you know, a long word. You can say I want to look in decimal and so on and so forth. And those things are persistent, meaning if we do them, we'll have to undo them, but we can say, for example, help X, and it'll show us, we can say X/format, and format could be any of these things, any of those things, and so on. But we'll rough it for now. So I'm going to create a sentinel, set the data field in the next field. I'll create a new node, set the data field in the next field. I'll create the sentinel's next field to, I'll change the sentinel's next field to point to new. I'll make a newer node, set the data to 100, set the next field to null, and I'll set the previous node new to point to my newer node. So if I print the sentinel, it's this value right here. If I look at that location, it's got 1, 2, 3, 4, 5, 6, 7, and then this funny memory address. And if I look at that memory address, that should be this node new. It's got a data field of 42. And then its next field is this other address. And if I look at that address, that's got a 64. Well, that's the hex value for 100. And that node's next field is 0. So with GDB, I can look in memory and I can see that the way memory is organized, starting with sentinel, corresponds to this picture. That would be cool to like link this to dialogue and draw these boxes. That would be awesome. That would be a great SLP, by the way. All right. So this is you know, playing around with code. This is not PA1, but these are the kinds of things that your functions in PA1 are going to want to do. But what are we doing to look at the list? We're looking at the value of sentinel. We're going to that location, and there's our first number, 1, 2, 3, 4, 5, 6, 7, not part of the list, right? It's the sentinel node. And then we're looking at its next field, and we're saying, hey, let's look at that. Let's go to that address and see what we've got. And if we go there, we see the number 42, that second node in the list, and so on. So here's the sentinel. Here's sentinel.data. Here's sentinel.next. I can say, let's look at the thing at that sentinel.next value. Let's look at its data. It's a 42. I can say, look at that thing's next. Well, this is the address where that newer node is. I can say, let's look at what's that at that address, look at that thing's data field. There's our 100. Let's look at its next field. There's our null. All right, so this is goofy. This is great notation if we're a Lisp programmer, but for C, this is a nightmare. So there's a different way that we can do this in C, and that's to use this arrow notation, a dash followed by a greater than sign. And this is just a shortcut, but it's a really good, convenient shortcut, and you're going to want to know this for doing anything in C related to pointers to structures. So if I say sentinel, take the thing at that address and give me the data field, I can do that with this different syntax, sentinel arrow data. This means that the arrow means, hey, data is a piece not of sentinel, but of the thing sentinel points to. In other words, start with sentinel, that's an address in memory, it's a pointer. Go to the thing it points to, and then give me the data field of that. So this means that. And instead of saying star sentinel dot next, I can say sentinel arrow next. All right. The reason that this is a convenient notation is, for example, if I know that sentinel arrow next is a pointer, I could say, let's take the thing that that points to and let's look at its data field. No, I don't have to do that. I can just say sentinel next. Let's look at that thing's data field. And this means exactly the same thing as that. So with that shortcut, doing this stuff we've been doing in here becomes a joy. So there's the sentinel itself. There's the data field of the sentinel. There's the next field of the sentinel. This is our next node. If I want to know that next node's data field, it's just sentinel arrow next arrow data. If I want to know that next node's next field, it's sentinel arrow next arrow next. Well, what is this? This is that newer node. And it's got a data field, and if I want to see what that data field is, I can just say this, there's the 100. And if I want to know what its next field is, there it is, it's a null. So this code over here we could rewrite this by saying, you know, new arrow next instead of star new dot next. And it's going to become a lot easier to read. It's going to become a lot easier to chain these things together, and it's going to make our code a lot cleaner. So that's the last sort of, you know, syntactic mechanical piece to this that may be new to you. All right, we're out of time. 2 hours and 10 minutes is a long time. We're packing these classes full with a ton of information, so don't worry if it's hazy. Don't worry if you feel like you only, you know, got 15% of this. There's a lot of material here, but meeting only 2 days a week, these are going to be dense lectures. So be prepared to go back and rewatch the videos, and also definitely come to office hours. Write some code, play around with this, and then come to office hours with some questions. And this is the whole course, right? Once we understand this, and we know how to use this notation, and we understand the idea of mallocing memory, that's the whole course. And we're just going to use that to do linked lists, different kinds of linked lists, stacks and queues and trees and search trees and all kinds of stuff. So the course gets a lot easier in some sense once we've got this platform to stand on and build from. All right, so we're out of time here. Have a good one. I'll see you in 2:15, or I will see you next week. I'll post something on Canvas tomorrow, letting you know if next week's going to be in person or continue as remote. All right, thanks.